gotta make this record. Hang on. All right. So we get to here. We get to the late 1800s. In fact, 1895. Wilhelm Röntgen and other researchers experimenting with a device called a Crookes tube that emitted something called a cathode ray. Okay, a cathode ray is a stream of electrons. Now, if you're looking here, where did we get the electron? 1897, we got the electron. Okay, so we're in 1895 in this right here in this story that we're telling. We didn't know that there was something called an electron. We knew how to use electricity to make a beam of something called a cathode ray, but we didn't know that it was really electrons that we were firing at things. Okay, but what they did know is that they could take this beam, and they knew that this beam, that they could create a beam inside of these things called Crookes tubes. So these things are about that big, roughly football sized. Okay, and you could take an electric charge and apply it to one end and the other, and in the middle of this thing called a Crookes tube, there was a bubble. You guys could see the bubble, and inside of that bubble, there were basically two electrodes separated by a gap. Okay. And in the bubble, they had removed all of the atmosphere. In fact, the thing that was usually done is they put inert gases, noble gases, in the tubes to displace like air. Air in the room would interfere with the electricity traveling from one electrode to the next. So you put inert gases like xenon or argon or krypton, any of these noble gases that you would see on the far right of the periodic table over there. And what you could do was you could apply electricity to one electrode, and it would arc. It would arc. Yes. Okay. It would arc the electric charge from one electrode to the other. You could make a stream of electricity. Okay, a beam of electricity. Okay, kind of like a welder would do nowadays, where they apply their little welding stick, and it arcs the electricity from the welding stick to the material, and it gives a little beam, little arc. Okay. And these things were called Crookes tubes, and so what they learned is that stream of electricity, it was arcing across from one electrode to the next. They learned it was electrically charged. Okay, they learned it had an electric charge to it, and they learned that opposite electric charges will repel each other, and like electric charges will attract each other. Okay, so they called the stream. They said that they just gave the stream a label. They called it a negatively charged. Okay, and what they said was that we can get this stream. Let's go to the next thing here. We can get this stream to be deflected, so we can actually push, and by applying electric charge, we can push this stream of electricity so it is oriented pointing out of the tube. And you could orient this stream toward things, right? And so one of the other nice things to do back then was experimenting with fluorescent materials that would light up when exposed to certain things like electricity or when exposed to certain types of light. You know, fluorescent materials now is like glow-in-the-dark stuff. Okay, anything that glows in the dark, right? When you hold it up to light and it glows, that's fluorescent. Okay, so what they learned is that they could take fluorescent material, cards of fluorescent material, and direct the stream at these cards, and the cards would light up in interesting ways, and they would do interesting experiments with that. They even learned that they could. This is Rankin and others learned that they could shield the tube, shield that Crookes tube, like put thick cardboard around the Crookes tube so no visible light is coming out. It kind of worked like a light bulb where visible light, like it would light up when they turned it on. So they could shield it from the visible light, and then they could still direct that stream of electrons through a thin aluminum window and still put cards in the way and still do their experiments, shield it with the tube shielded. Okay, so they say researchers routinely surrounded the tube with black cardboard so that any light generated within the tube would not be confused with light emitted from the fluorescent cards. So that's where we're at now. We're at the point where scientists had been able to kind of harness electricity in a way where they could do experiments with it. They learned that they would get better results if they shielded their tube, okay, and blacked it out so no visible light was coming out of that. So any light that they saw was coming from their little fluorescent material cards. And they were trying to learn about matter and material, right, how it behaved. They would do things like increase or decrease the voltage, increase or decrease the power going through the Crookes tube, which would change the way that the light was emitted from the cards. It would change the color of the light emitted from the cards and so forth. During one of these experiments, November 8th, 1895, this is for radiographers, this is our most important date, okay? It is the day in history when X-rays were discovered, all right? So we got to remember this one, November 8th, 1895. You're not going to forget it. In Germany, because he's a German physicist, he notices that, so we got cards, right? We have these cards of fluorescent material that we know will light up when we direct our electron stream directly at them, okay? But when we put our cards over here on the other side of the room, they don't light up because we're not directing the stream directly at those cards. However, he, in his experiments, had adjusted the voltage of his Crookes tube to high enough voltages to where when he directed his electron stream at the cards that were, let's say, in your guys' direction, over here, the card on his table began to light up. And he's going, what the heck is going on here, right? What he has discovered is that he has created a beam, a type of light that can, and I'll just kind of give it away, that can travel through the material, travel through the black cardboard, right? We couldn't see it going through the black cardboard, right? But it was affecting this material over here. He discovered a new ray, a new type of a new beam, a new type of light. Okay, it's an accidental discovery. It's one of those several accidental discoveries in science, right? It's the Newton having an apple fall on his head and understanding that is he didn't understand gravity. He understood gravity, but understand that that's the same force that makes planets move around the sun, right? So it's like Newton's accidental discovery, Röntgen's accidental discovery that he found a new thing. Okay. So Röntgen realizes that there must be some type, because things don't just light up on their own, right? And so he would do things like he would turn the machine off, right? And when he turned the machine off, the paper would stop glowing. Turns the machine on, paper stops glowing. So he develops, there's a cause and effect here, right? He must say that, this is only being affected, this paper over here is only being affected when I turn my machine on. There must be some type of energy coming from my Crookes tube going through the cardboard, the shielding cardboard, and lighting up that paper over there, okay? So he realizes there must be some other form of radiation being emitted from the box in all directions. Presumably, they don't really say this explicitly, but presumably he took that paper and moved it to different points in the room to see if it was affected the same at all the points in the room. And so he discovers, oh my gosh, there's a type of radiation coming through this cardboard box, traveling in all directions, and it's making my paper light up no matter where I put the paper in the room. Okay, so when I apply this type of energy to the Crookes tube, direct the electron stream at whatever I'm directing it at, it makes this paper light up no matter where I'm at in the room in relationship to the tube. He doesn't know what to call it because we didn't know about any types of radiation that we couldn't see or detect with human senses, so he calls it radiation X. And we have just taken that and ran with it and called it X-rays since then. Okay, so they say in a series of brilliant experiments, he is able to determine that unlike visible light, X-rays travel in straight lines. Okay, we know that visible light bends because we can do things like the double slit experiment, which again I will get to showing you, or I can pick up my bottle and I can look through my bottle at you guys, right? I can see through that bottle. I can see Sarah through that bottle. I know she's there, but I don't have a good picture of her. I got a very blurry image of Sarah when I'm looking through this bottle. Why? Because the light coming from Sarah through this bottle, through the water in the bottle, is being bent, being refracted. Okay, X-rays don't do that. So Röntgen discovers that X-rays travel in straight lines, unlike visible light. X-rays are stopped by lead. X-rays could cast a shadow. So he would take, you could take that fluorescent card that he was using, that he noticed that would light up, and he could put his hand in the way of the fluorescent card, and notice that anywhere where his hand was, the card wasn't lighting up. Okay, so he could cast a shadow of his hand on the card. He also happened to find out that because he's, this is the thing, this is a type of radiation he doesn't know about, but he knows about other types of radiation. He knows about visible light and so forth, and they had cameras, okay? So they had photographic film. So he takes a piece of photographic film, and he asks his wife, put your hand on the photographic film, right, on the film, and I'm going to turn my Crookes tube on, okay, and we're going to see if we can make an image of your hand, if we can expose photographic film with my new X-ray. Okay, and so this is the first radiograph ever taken. This is the field of radiography being born. It's never said exactly how long after November 8th that he does this, but I'm assuming pretty quickly. He puts his wife's hand on a piece of photographic film. Her wedding ring's still on in this picture. And he turns his Crookes tube on for 4 minutes, turns it off, and then processes the film. Wet dip processes the film, right? It's 1800s. And develops it. And oh my gosh, we can see the bones of his wife's hand. We can see the big metal area where the ring is, the gold or silver, whatever that ring is made of. We can see the bones of her hand. We can see where the bones are denser or less dense. See, the white parts are evidence that there's denser parts. So this is the first radiograph ever taken, and it was taken on Röntgen's wife's hand. And she had to sit still for 4 minutes for this. Okay, I mean 4 minutes is not a long time, but it's way longer than any amount of time people have to sit still for a single X-ray exposure nowadays. X-ray exposures nowadays take milliseconds, thousandths of a second. Okay, so that's important. The field of radiography is born after Röntgen realizes, oh my gosh, I can use this X-ray to expose photographic film and take pictures, radiographs of the inside of people's bodies. We can radiograph bones and things like that, bones and joints and other parts of the body now. Okay. So, to be clear, Röntgen discovers man-made radiation. Okay, radiation that we created with our machines. Okay. Kind of weird, right? We discovered man-made radiation, and then the next year, we discovered that in nature, there's natural radiation already happening. Okay. So Henri Becquerel does another one of these also by accident kind of discoveries. Okay. So you guys had Henri Becquerel right here. Okay. Henri Becquerel is credited with discovering natural radioactivity, again by accident. So this time this scientist is experimenting with something called phosphorescent materials. It's kind of like fluorescence. Fluorescence is more like I shine a light on a material and it lights up, and then when I turn the light off, it stops lighting up. Okay. Phosphorescence is more like I shine a light on a material, turn the light off, and the material continues to emit light. Okay, to glow. So he had materials that would glow in the dark after absorbing sunlight. And it's said that on a cloudy day, and so the way he did his experiments was because he couldn't always very well see the light, and the way they would quantify how much light a material emitted was by taking the material, exposing it to sunlight, and then putting a photographic plate near the material, and then exposing the photographic plate to the glowing material, processing the plate, and seeing how much exposure the photographic plate received. That was the way they could quantify their result. So it said that on a day, he was frustrated and he put his phosphorescent materials away. Took his photographic plate and put it in a drawer. It's a cloudy day, so he couldn't use the sunlight. And wraps up his photographic plate, puts it in a drawer with other things, and in that drawer was some crystals that he had been experimenting with. The crystals were nice because they would emit light in interesting ways, but he didn't know much else about the crystals that he's experimenting with. Turns out that these crystals that he was experimenting with were radioactive, probably uranium or something like that. But it said that later, on a whim, assuming he's like cleaning his shop, something like that, opens the drawer, finds the photographic plate, and decides maybe I should process this and see if anything has happened to it. Okay, and he discovers that the plate had been fogged, and he through his deduction decides that the only thing that could have exposed that plate in that drawer was this crystal in the drawer. Okay, so he concludes that there must be something being emitted, and he called them X-rays too. He's saying that there are X-rays being emitted from this crystal. Okay. Later, these were shown to not be X-rays, but to be things called alpha, beta, and gamma particles. He discovers natural radioactivity, particulate radiation in this. And remember, science is reproducible, so this experiment has to be able to be reproduced, and so we have to assume that he himself reproduced the experiments, and others did, or they would have falsified his experiments. Okay, again, that's how we work. So Röntgen and Becquerel receive Nobel Prizes. Röntgen discovers man-made radioactivity, X-rays. Becquerel thought he rediscovered X-rays on accident, but actually discovered particulate radiation, which was hugely important, which leads to people like Rutherford discovering things like the proton later on. Okay, so really important that he discovers natural radioactivity. And so what we say is Röntgen's work began a revolution in physics that included understanding the nature of the atom, so further understanding the nature of everything. And later on, Ernest Rutherford, who's we have here as understanding and telling us about the Rutherford atom, and in 1919 discovering the proton, he figures out that the type of radiation being emitted, he's the one who figured out that the type of radiation being emitted from Becquerel's crystals were called alpha, beta, and gamma particles, and he discovers that an alpha particle is really just the nucleus of a helium atom. Okay, helium, you guys know about helium. Helium is the thing that we put in balloons, right? It makes balloons float, right? Because it's lighter than air. But helium is a nucleus where there are 2 protons and 2 neutrons, and he discovers that the alpha particles being emitted from Becquerel's crystals were equivalent to a helium nucleus. If that doesn't mean anything to you now, it will it will eventually. But in this is the 1919 thing. In this, he proves the existence of the thing called the proton, predicts the discovery of something called a neutron, which we later found. In 1905, Einstein discovers the photoelectric effect. Okay, so this is no good historical order, this last statement here. But again, a revolution in physics after Röntgen and Becquerel make their discoveries, right? This was the end of the 1800s, a big tipping point in our understanding. So we've really started to ramp up our understandings. So 1895, remember that date, okay? The first diagnostic X-ray unit to take X-rays of people, okay, was installed in a hospital in Massachusetts in 1896. Okay, so 1895, at the end November, we're almost to November 8th. We're almost to one of the anniversaries of Röntgen's discovery. But 1896, less than a year later, in the U.S., this was in Germany, remember, Röntgen's in Germany, okay? Less than a year later, in the U.S., we have installed diagnostic X-ray units, okay? So that's how quickly this spread. Huge discovery. All of a sudden, everybody wants to use X-rays because Röntgen figured out that you can use X-rays to expose the body. You can take pictures of the inside of the body, okay? And that's huge information because prior to that, I mean, what did surgeons and physicians have prior to X-rays? Nothing, right? They had palpation and manipulation. They had auscultation, percussion. They could knock on the body and hear things. They could move body parts around and hear things. Like they could take your broken wrist and they could kind of move it around a little bit and hear your broken bones scraping together, right? They go, oh yeah, the wrist is broken, okay? But they didn't have a way to image the body. There was no ultrasound. There was no X-ray before that, right? And so, yeah, right away, people want to start using this to do interesting things with, to do medicine with. Okay, so big, huge revolution in medicine from there on. And so here's what's neat. Maybe not neat for this guy, but there he is. He's getting an X-ray taken of his shoulder. You can see above his shoulder, and it's a little grainy, but you can see the Crookes tube here. Okay, there's the ball of the Crookes tube. There's either end of the Crookes tube, and here is a lead cone. It looks like a top hat. It's got the brim of the hat, and then the tall part of the hat. But what that is, it's a device called a collimator. Okay, so under his shoulder here is a photographic plate, what we would now call an image receptor. Okay, and they turn this on. This thing emits X-rays in all directions. Okay, so what they do is they put a big disc right here. Again, it's like the brim of a big top hat. Okay, they put a big disc right here to block off the X-rays that are traveling in weird random directions, and only allow X-rays to hit the film that are traveling down through this cylinder, down through this collimator. You guys have had dental X-rays, right? You know that when they put that thing up to your face, that tube, right? That's the collimator. It's the same thing, okay? And so this is 1896, the first diagnostic X-ray machine. Interestingly, he's covering his gonads. He didn't know to do that, Okay, he must have had some innate understanding of the dangers here. We didn't know about the dangers until about 50 years later. A solid decade later until we really had any idea, and then at least 50 years beyond this till we had a really quantitative understanding of what was happening here and actually putting in real guidelines for protection. But he was interestingly protecting himself. That might have just been where he decided to put his hands. But yeah, so that's the first use, diagnostic use of X-ray. So 1895, November 1895, Röntgen takes the first radiograph of his wife's hand, and less than a year later in the US, this is being used to actually diagnose disease in patients. Traumatic disease, probably fell and bumped his shoulder or something. Okay, but yeah, I mean, this X-ray tube is unshielded. It has a very crude collimating device. And the photographic plate used to make his image probably required that the image takes a couple of minutes to expose. Okay, where nowadays we can do much better than that. So this is kind of where we came from. So let's talk about where we are going to. This next section.